The Secret of Flight, a series of programs on aerodynamics. The subject of today's program, the 10th in the series, is lift theory and high lift devices. And now, here is your host, Dr. Alexander Lippisch.
In our last program, I have shown you this flying stick, the rotor. And I think it might be nice to show it to you again now and fly it again here in our studio. You see, this line we have wound around, this gives this rotor a rotation this way around. That means it rotates as if it would roll on a surface above, just opposite to a wheel which would roll on the ground. And you see, when I let it go, it flies now very nicely. How does this happen? And how does this come so? Well, let's think about it. We have a circular cylinder. And when we rotate the circular cylinder, then the air which is around the cylinder will also begin to rotate, so that we have what we call a circulation around this cylinder. Now, if we move this thing forward, then this rotational motion, in this way now, move it forward, this rotational motion would add to the forward motion. And since we have here, for instance, the cylinder which goes above due to its rotational motion above this way and underneath this way, the forward velocity against the cylinder would add here to the velocity on the upper surface and underneath diminish this velocity, so that we have a difference in speed above and below. Now, if you remember, when the speed increases, the pressure decreases. When the speed decreases, the pressure increases. So, up there we have more speed than average. Down there we have less speed than average, and this gives us up there lower pressure, suction, down there more pressure, and the thing is resultant as a lift force. And the flow which we have here, if we would think that we would have no friction in the fluid, would look like this. And go over here and produce a lift normal to the flow direction before this thing hits the rotating cylinder. Now I can show you the same thing in our smoke tunnel. And we have here a cylinder in it. And when we make the flow lines and then begin to turn the cylinder, which now runs, the flow comes from this side, runs around this way, then you will see that at once an asymmetrical flow field develops, which you see, come on, run it now, where you see that the velocity above is higher, the lines are more narrow, and the velocity below is lower, and the lines will be wider. Now we will begin to rotate this. I will go out of the flow field so that you can see it. Now we have the cylinder in the tunnel and we begin to rotate. Look at it. The more we have rotation, the more flow lines are pulled over the upper surface of the cylinder, and you see at once that our speed is very high above and quite low underneath of the cylinder, which gives us a lift normal to the direction of the flow. Now, you might ask me, what has this to do with a wing? What has it to do with the lift of a wing? This is no wing, and we cannot fly with such a rotor. Or we will have quite a bit of drag, because you see here this much wake behind the cylinder, which necessarily indicates that there's lots of drag. Well, the main point which we have here is this, that when we have circulation and translation, translation means here a straight motion, a straight continuous forward motion. When we have circulation and translation, then we will have lift. And the interesting thing is this, that a wing produces this circulation without such gadgetry as we use it here, first to rotate the cylinder. The wing, which has a very special shape because it's round in front and sharp at the rear. This wing, due to this sharp corner, develops a flow which you, as well as we did it on the cylinder, can take apart into a circulating flow around the wing and a translation which gives you then finally the flow picture which shows you the lift of the wing. So actually the lift of the wing is in the same way developed as we develop the lift on the rotating cylinder. Now look at the wing here in the tunnel and see, when I change the angle of attack of this wing, then I increase the lift in the same way as we would rotate more and more the cylinder. But you know, this has certain difficulties, because to increase the lift only by changing the angle of attack of the wing would mean that you have to change the whole attitude of your aircraft. So if you want to fly slow, which you necessarily need in takeoff and landing, well, then you had to tilt up your plane quite a bit to get this higher lift. And especially if you have passengers in an airliner, or you have other kinds of freight or something in your fuselage, you wouldn't like to change this attitude so much. You are much better off if you could fly your fuselage straight and still change your lift. How you do it? Now you change part of the wing in angle of attack. You change only the rear part and give him a larger angle. And this is what you see here. See, when you make a flap back there, as we did it here on this model, then you will see at once that if I change the angle of the flap, we also change the lift and have the same effect. You see it here? You see that the moment I change the flap, the moment the more streamlines go over the wing. That means the higher is our circulation. Look at it once again. There we are. There we are. And you see, a flap therefore acts in the same way as the change of angle of attack. Now, you see, as long as we have that wing in this position, this increasing the lift with the flap is all right. But it might sometimes happen, you know, that you have your airplane in a different condition, and you might have it even pulled up So it might sit something like this, which is not too far from the stall. When you now use your flap, what happens then? Then the airfoil doesn't take it anymore, and the wing as such stalls out, which is quite dangerous, especially if this flap, for instance, is on the outer part of the wing, and you put one flap down and the other one up, and then this one, which you want to get up, stalls out and comes down, and, well, you know what happens then, huh? You call it timber. Anyhow, how can we change this? Or what can we do to prevent the stall under such conditions? Now, two fellows, Sir Lippisch and Dr. Lachman, they got this idea during the First War, and the thing is this. You see, when I have it in this position and I put the flap down, the flow cannot follow anymore this upper curvature. We have this wing here, and the flow cannot go around here and stalls away. And this is a dead air zone. Now, to prevent this, what could we do? We could probably make a slot into the wing and let some of the air from underneath go into this dead air zone and blow it away. And we actually have a model of this type here. See, a model where we have what we call a slot on the nose. And I can operate the slot in this tunnel. And then you will see that we can prevent the stall with it. Now, this method of having a slotted wing is not only used for preventing the stall on the nose, where it's now, as you see it on fighter wings, for instance, used to prevent the stall when you make a tight turn and you have a kind of an automatic slot which kicks out when you have this high angle and prevents the stall. But you have also wings where several slots are one behind each other. And remember what you have seen in nature. A bird has this in its outer so-called primary feathers. And he prevents the stall with the same method than we have it here today on the airplane. Now we have this model in the tunnel. And let me demonstrate to you how such a slot actually works. Let's first put it into a position where when we deflect the flap, the thing stalls out. Now if I move out the slot, then you see at once that part of the air is vented into the upper surface and prevents the stalling of the wing. See it? Here, once more. Now you can make this going automatically, and in this way you can even prevent any dangerous situation even if the pilot is not able to think about it. But the trouble with the slotted wing is this, that due to all this machinery which you need, you have quite a bit of drag on it. And it causes more drag than a smooth wing, which is obvious. So people have looked for some other means of making high lift, especially since we have developed into a stage of aircraft designs which now reaches into such high speeds that our true difficulties are in the low speed range, where these high-speed aircraft still have landing speeds which are way above 100 miles per hour, and you need long runways and big installations to make the thing going up and coming down. Could you do something about this? Then you should do first some kind of artificial lift. Now think what happens here with the stall. When you think about it, as I showed you, this flow disattaches from the upper surface. So how could you bring it back? Well, you could bring it back probably in taking this air, which has lost its energy, which has lost its momentum, take it away. Make some little slots in the surface and put suction into the wing and suck the dead air zone away. And then it would stay attached. This air zone, which is here between the wing and the surface, as you know, we call the boundary layer. The layer which is in the boundary between the wing itself and the outer air. We suck part of this boundary layer away, and in this way achieve a very high lift. I have here a model in this tunnel which has little slots on its surface, actually several ones. Here one in front, the next. These are 5 different slots, and you will see that when we now first give it a large angle of attack so that it stalls, and we put suction on it, then it reattaches, and we can go to very high angles of attack to prevent the stall, as you see it here. You see, now I can go quite a bit up with this wing until it stalls. And when I do this boundary layer suction very slowly in the normal range where we want to fly with high speed, then I even reduce the drag with it, because the dead air, which has lost its momentum, will now be sucked in and accelerated through the blower system. This has advantages, many advantages, and was, well, proposed long time ago. Actually, it was one of the first products of the boundary layer theory, which was founded by Ludwig Prandtl in 1905. So 50 years ago, this system was proposed and is not as yet in use. Why? Because in the meantime, where we really need to apply it now with the high-speed aircraft, the wings got so small that there is no space inside anymore for putting these large ducts in it to suck this boundary layer away. Because when you suck, well, then you need a large duct, because this air which you suck in will have low pressure and a large volume. So is there probably something else to do? And is there probably another method which would be, from the standpoint of design of aircraft, from the standpoint of engineering, easier to be used? Well, there is. And this is just the opposite to this boundary layer suction. It's blowing, because, see, you could also accelerate this dead air zone, this mass of air which has lost its momentum on the surface. If you would blow to it, well, then you would get almost the same effect. And let's look at another model which has now a blowing slot on the surface. Now we have a section in the tunnel which has on the upper surface one slot where we blow out the air over the upper surface so that we can now accelerate the boundary layer and in this way get it attached, reattached. You see, I start it now, and when we now blow, you will see that it reattaches. It actually, at this point, it's really a little bit too much blowing. But you see that at once we have a very large lift. Now you can see this even better if you look at a slow motion film with pulsating smoke, which we have here. And there you see at once how fast the flow moves over the upper surface. And as you remember, the difference between the smoke lines on the upper surface and the lower surface is a measure for the circulation. And you see here how much circulation we have with this blowing slot. Now you see this blowing has the advantage that you can lead the air to the blowing slots through small lines, and in this way it saves space and has a much more practical application. Now you don't need the blowing just for making high lift, but you can also make kind of an invisible flap by blowing out at the rear end of the section. That's what they now call a jet flap, a section where here is the tube in it and we blow out this way. And this layer of air then works like a jet flap, as you see it here. You see now we have at the end of this section, we have a tube and we blow out of the tube, and in this way we increase the lift and we also can control the lift of this section all over. Now if you go farther, you would think of using such systems in many ways and making a body which makes now the lift in the way as we originally thought about it. So what could you do, for instance? You think we had first the rotating cylinder, completely round. Now you wouldn't fly with such a thing, but probably you could do this. You could take a more elliptical cross-section and make this big thing, which is easy to build, lift. What you would do then, you would blow out air over the upper surface and probably at the rear to make the circulation going and achieve in this way a configuration which gives very high lift. And this high lift with a cross-section which is easy to be built and constructed. We have such a section which we call a super circulation section, an artificial circulation section in this tunnel, and I will show you how it works. Now if we turn the smoke on, we will see the flow as it is without blowing. Now you see this flow with this super circulation. We have almost achieved the picture which was once predicted by the theory, where we have here and there a stagnation point, very low speed underneath and very high speed above. We can do that artificially with blowing over the surface. We have also a high-speed film of this, and we can look at it and see how the timelines are now quite wide from each other, and we can see the large amount of lift which we can achieve with such a section. In our next program, we will talk about something really interesting, And I will just show you a little experiment which might make you thinking. See, first I light a candle. Now it goes. I put it here somewhere. So, and now somebody wants to blow the candle out. I don't need to go there. And there you are. Now what is it? What I shoot there through the air? It is a vortex. And you might even see it here with this little gadget where we have smoke in it. And when you look at it, then you see that there are all vortices coming out of this. Well, this is the smoke ring, as you know, is used very often for demonstration, and which actually is one of the main examples of a vortex. And when we think about what we saw today, that circulation around the wing is in some way nothing than making a vortex which is now bound to the wing and with the translation makes the lift. The main thing is this, that a vortex behaves in air as if it would be a solid body. We will look at many applications at our next program. Goodbye and auf Wiedersehen.
Just seen lift theory and high lift devices, the 10th in a series of programs explaining the secret of flight. Your host has been Dr. Alexander Lippisch, Director of the Aeronautical Research Laboratories of the Collins Radio Company. This program was produced for the Educational Television and Radio Center by the State University of Iowa.